Hello again, folks, in 113. Today we're going to be covering section 11.5. Just to verify here. Okay, today is Tuesday, April 27th, so 11.5 per the schedule. Okay. The packet that I have for you today looks like this. Okay. This is an overview, sort of a worksheet I made. Right? I left it blank. I'm gonna have basically do this like I normally do, project it and then write on top of it. So if you're following along, print this out. It will summarize basically the whole section, but I want to write the formulae across this, okay, and then maybe give you an example briefly underneath. Okay. There's the material. If you're more content, swipe from the textbook. It basically says the same thing. There's the formulas. The formula, and here's the second one. And there's some terminology. But I like my diagram. Not to corrupt you, I'm hoping it helps. Anyhow, there are several examples. I'm going to go through each of these. I left the solutions because they are tricky. I think that's it. All right. The real essence of everything is, again, as I said, this page. Okay, so we'll go through that. Hopefully my eyes will be up to speed here. You know what? I left my glasses upstairs. Excuse me a minute. I didn't move this too much. Looks like it's okay. There you are. Okay. Good. Let me turn the projector. Or not. Let me see. Yeah, I think it will. Alright. While this is booting, I could definitely plug it in. There you go. Let's go for this page. Okay. All right. The subject of 11.5 is something collectively we might refer to as compound inequalities. Compound probability. Not really awake yet. That's too much. All right. It's often inconvenient, right? That is to say, time-consuming to construct a tree diagram if you're trying to figure out the sample space. That was the subject of 11.4. It's useful, right, but it can be tedious, and an example of that would be to say if you were selecting two cards out of 52, right, consecutively. Right. That, according to the counting principle, would mean that you have m number of outcomes for the first event times n number of outcomes for the second event, which means consecutively, and then there's this phrase, I should add with replacement. This will be even worse. If I put the card back after I pick the first one, That means that there's 52 outcomes for the first experiment and 52 outcomes for the second experiment, which means that in the sample space, the total number of basically permutations would be 2,704, which, if you did a tree diagram, right, not impossible, but it would be quite arduous, right? So rather than do that, what we can take advantage of potentially are compound probabilities. So with that in mind, let's discuss these. Right. English, just to preface, you probably know by now, especially in the position of teacher, all right, it gets you in trouble a lot. So you have to be very careful and try to be precise 100% of the time. It's not always easy, of course. Sometimes we speak in vernacular English and everybody knows what you mean, but you want to be as precise as often as possible. Anyhow, these English words, or and actually pertain to something. All right. In general, the word or, if it is written in the context of some problem, all right, is a discussion of mutually exclusive or not mutually exclusive equations, okay, formulas, right, probability formulas, right. They are together sometimes referred to as the addition rules because they involve adding, right, and in this case subtracting. If, on the other hand, you see the word and, which sometimes I didn't even bother to write it, but you can kind of tell depending upon some other circumstances, and we'll go through some examples. And it implies basically the dependent or independent equations, right? We've kind of really done this already, all right? But we're going to delve in a little bit deeper, all right? We really didn't go into the discussion of whether the situations described in 11.4 were dependent or independent. In some cases, they might have been one or the other. Anyhow, if you have a dependent equation, a dependent set of circumstances, you might see the phrase without replacement. If you have independent, they will say, just as in the last example, with replacement. And what that means is that the first event, or the first game, has no bearing upon the other. All right? They're completely independent of one another. On the other hand, if the second event is affected by the first, all right, which means that the pool from which you would draw cards is somehow minimized or diminished. All right, that means that the first event is affecting the second event. All right, so you would call the situation dependent instead. Okay, anyhow, this involves multiplication. Right, basically similar to the counting principle, except that you're going to see fractions rather than whole numbers. Okay, so. You might remember, I don't want to really bog you down with this, but you might remember Venn diagrams. And that was discussed now. I'm struggling to remember. That was MAT-113, and you guys are in 113, so yes, you would have seen this at one point earlier in the semester. Venn diagrams, when you see the word and, right, and that's still the case, that implies an intersection, right, which is symbolized by sort of a horseshoe shape or an upside down U, if you like. Let's see if this is bright enough. I think that's okay. And that means that we would be interested in an overlap only. In the context of probability, that's still basically true, right? That's why I put this thought cloud here. Both situations described need to be a success, all right, when you have some and situation, all right? If you have an or situation, which is more akin to union, all right, either is considered a success or a win, all right? So we'll get into it, all right? let's see. Here's the formula, firstly, for this situation. When you know that you have an OR type of problem, you'll see the word OR. And you've decided whether things are mutually exclusive or not. What does that mean? Well, if something is if two things are mutually exclusive, it means that they cannot coexist. They cannot happen at the same time. All right? So you have to get in the habit of asking yourself, can these things occur simultaneously? If they can occur simultaneously, then they're not mutually exclusive. It's kind of an awkward way of thinking, but it's true. All right? If they cannot occur simultaneously, then they are mutually exclusive. And were that the case, this is the model. Right? The probability of A, as in the first event, and then you'll see the word or, B, is equal to the probability of A, the first, plus the probability of B, the second. That's probably the least complicated of all formulae. Okay. Now, as an example of that, I'll just write it under here. This is visible. An example of this would be like the probability when you're playing with drawing playing cards. The probability of drawing, say, an ace or a queen out of a deck of 52. All right, if you wanted to summarize that, you might say P parentheses A or Q. All right, now let's discuss mutual exclusivity, if that is even a phrase. All right, can a card be both an ace and a queen at the same time? They can't. It's either this or it's that. In which case, they cannot occur simultaneously in the form of the same card, and therefore they are mutually exclusive. So we will use this red equation here. Okay? So, if you're calculating the probability as a fraction, as you should, of drawing an ace, how many aces are there in a deck of 52 cards? There would be 4 out of 52, right? Right. How many queens are there in the same deck? There are 4 out of 52 as well. Okay. And as long as we're using this word or, this is perfectly acceptable to go with this formula. Anyhow, the sum would be just the tops, of course. So it'd be 8 out of 32, which if you reduce it would be 1/4, 1/4, or 25%, right? What is the probability of drawing an ace or a queen? 1/4. No, wait, I'm sorry, it's not over 32. I'm wondering why that looks suspicious. Forgive me. More coffee definitely needed. If you divide, let's see, 8 by 4, you would get 2. And if you divide 52 by 4, you get 13. So it would be 2 out of 13. That is definitely more reasonable. This is about 15%. If you divide 2 by 13, you get 0.15 something. So 15%, which is not that great. Right? But anyhow, this is the formula that you would choose based upon whether something is mutually exclusive or not, and they must use the word or. Okay. Right. Now, in this situation, not mutually exclusive. I don't know how faint this is going to be, so let me just test it ahead of time. That's pretty good, actually. The formula that we would use in this case is the probability of two events, so A or B again. But this will be a little bit longer, so I'm going to cheat and I'm going to write it under here because I have short on space. Okay. In this context,
you'd have to account for the situation where something does occur simultaneously. So what you will see is almost the same formula, but then an extra term. Is that visible? Is that making it better or worse? It might actually be helpful. Making this a little bit dimmer. Alright. If necessary, I will darken this. This is the probability of the first event, let's just call it A to generalize, plus the probability of the second event, B. And then in the situation where two things can occur simultaneously and therefore they are not mutually exclusive, you have to subtract out the situation where that thing occurs at the same time. So there's an extra term of minus. All right, so you would subtract out the probability of A and B. All right, this is so you don't count something more than once. This extra term is so as you do not count more than once. All right. Now an example that would be something like that. Yeah, I'll do this in blue. An example pertaining to this would be the probability of, I'm going to use my abbreviations, the probability of drawing a heart, I mean literally pulling it out of the deck, not physically drawing it, or a face card. If you think about it, can a card from a deck be simultaneously a face and a heart? Right, and here's my deck of cards here, so let's see if that is true. Can a card be both a heart and a face? Yes. All right. Here's a face card that is also a heart. All right. How many of these are there, though? There should be 3 heart face cards. Jack, Queen, King, right? So, if we would be appropriate to use this equation where they're not mutually exclusive because they can occur simultaneously in the form of the same card. We will calculate these two probabilities independently of each other. All right, and then subtract out the instances of when they are the same thing. So the probability of a heart for A and a face for B. And this will be a heart and a face. So in this instance, the probability of drawing a heart. How many hearts are there in a deck of 52 playing cards? There should be 13, I believe, right? Yes. All right. 13 out of 52. Plus, how many face cards are there? Less, right? There's 3 of each suit, and there's 4 suits, so there should be 12 then, right? 3 hearts, 3, there's 3 jacks, 3 heart face cards that are Jack, Queen, King, another 3 that are the spades, another 3 that are diamonds, another 3 that are clubs, so that is 12. I think I'm going on camera again without having a second cup of coffee. Okay, now, how many of the cards are there that are simultaneously a king, a heart, a heart and a face card? I'm ripping them out here. There are just 3.
So you have your queen, jack, and king here, not in order. But these are face cards that are also hearts. So, because technically we've already included them in this figure, right? Because there's 13 hearts in general, we don't want to count them more than once. So what we have to do is we have to subtract out the situation that is these extra 3. Right. They are accounted for basically in this set and in this set. Okay. They're accounted for in this set as being part of the hearts. They are accounted for in this set as being part of the face cards. So anyhow, if you follow the commutative property, which is to work from left to right, addition and subtraction being equally important, so we're going to just do 13 and 12 is 25. Then if you subtract 3, what do you get? You get 22 out of 52, right, which divide by 2, each of these, you would get 11 out of 26, which is 42% if you changed it to a decimal, and then a percentage. Right, not bad, up from 2/13. Okay. All right. Before I do these two, I want to do the examples that pertain to these. I think when I come back to this slide, what I'll do is I'll just enlarge it, so they don't have. It's hard for me to sort of write what the mark is that I have here. All right. So you have these two formulas, and these are the two that you're going to be electing from. All right, for the examples that you will now see. Okay. Now with that, let's look at example 1 here. Get rid of the thumbnail here. This is why, again, I mentioned the conversation about Venn diagrams, because in the first couple of examples they bring them up again. You don't really need them, but they're a visual aid, so they might help. This is being so much more cooperative today. I don't know why. What's up with these? If you were to read this, right, each of the numbers 1 through 10 is written on a separate piece of paper. The 10 pieces of paper are then placed in a hat and 1 piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or telltale sign, right, or right, a number greater than 6. What I would encourage you to do is get in the habit of taking the word problem and trying to rephrase it correctly, just more concisely. So essentially what you are asked here is, what is the probability of selecting an even or a number greater than 6. Right. That is essentially the question written in one sentence. Right. This is example 1. Okay. Now, if you like, go ahead and utilize the Venn diagram. To me, you don't really need to do that. What I would encourage you instead to do is write out the set, basically, of these numbers. That to me is a more useful visual aid. So if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we can decide, are these mutually exclusive or not? Ask yourself,
can a number be both even and greater than 6? Right? And you have this visual aid here, the actual set of the numbers involved, to analyze that question or to answer that question. Well, where are the numbers bigger than 6? All right. From here onward are the numbers that are greater than 6. All right. Are any of them even? Yeah, that one is even and that one is even. So they can, yes. All right. You can have a number that is both even and greater than 6. So therefore they are not mutually exclusive. Which means that which formula we're going to have to use? Right? We're going to have to use the one that involves subtraction to account for counting something more than once. So here is that formula again. Taking the original question and sort of simplifying it. The probability of an even or a number greater than 6. I'm just using n to represent number. And you could use the capital E if you want in place of even. Right? To generalize would be the probability of an even independently plus the probability of a number greater than 6. And then because they exist, that those figures coexist in these two situations, we're going to subtract so that we only count it one time. The probability of something that is even and greater than 6. Okay. All right. Now let's figure out the fractions in each case. All right. How many evens occur in this set? 1, 2, 3, 4, 5. Right? So for this portion here, it would be 5 out of 10. How many numbers are greater than 6? 1, 2, 3, 4. So this is 4 out of 10. Right. How many numbers are even and greater than 6 at the same time? 2. Right. So this is 2 out of 10. Right. Follow the order of operations. You know that when you have the common denominator as 10 already, you don't have to do anything but add or subtract the tops, the numerators. So 5 plus 4 is 9. 9 minus 2 is how much? 7 out of 10. So 70%. Okay, not too bad. All right. Let us see. All right, let's look at number 2. Another situation where you have a Venn diagram. Consider the same sample space, the numbers 1 through 10. Okay. So that was this. This is example 2. And we're going to borrow the sample set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. In fancy braces. I'm sorry if that's a bit faint. What else? 2, there we go, that's a bit better. 6, 7, 8, If one piece of paper is selected, determine the probability that it contains a number less than 5 or a number greater than 8. Okay. So we're asking, and notice there's an or here as well, the probability of a number less than 5 or a number greater than 8. That is to make this more concise. Alright? Once again, ask yourself, alright, can a number be both less than 5 and greater than 8 at the same time? Simultaneously. That's the end of this. Can a number be both less than 5 and greater than 8 simultaneously, occurring at the same time? And the answer to that should be a resounding no. No. Alright, and therefore they are mutually exclusive. Right, which just dictates which formula that we're going to use. Alright, so the formula in this case would be the probability of a number, I'm going to use n again to abbreviate, less than 5, or a number greater than 8, would be just two things added. The probability of a number less than 5 plus the probability of a number greater than 8. Format of this set that is very faint up here. All right. So to establish the first fraction probability, let us count the things that are less than 5. Right? Everything from here on back is less than 5. Right? 1, 2, 3, 4. So this is 4 out of 10. Right? And everything that is greater than 8 is just from here to here. Right? So it's just two things. So it's plus 2 out of 10. Right? If you add these, obviously, what is 4 plus 2? 6 out of 10, which if you lower the terms of the fraction, and if you ever get an answer wrong, it just may be that it's not simplified. I don't think they should take points off for that, but just beware. You're not wrong, you just have to simplify. Divide each by 2, you would have 3 over 5. So 60%, right, 3/5 probability, okay? Which is pretty good. No, these are mutually exclusive. Okay. Now, for example 3, it's sort of rapid fire, but it's still the same situation. So, first this without throwing things. I might turn off the projector now. Let's see. Let me just show it to you first, and then I will, just for the sake of space, turn this off. All right. Example 3. One card is selected from a standard deck of playing cards, 52. All right. Determine whether the following pairs of events are mutually exclusive, all right, or not, and then determine the probability of A or B. All right, and there's 4 of these. So I'm going to turn this off, right, and then sort of just answer the 4 of them on the same board here. Okay.
the curtain here. Put it in the right. Turn that on. Okay. So, example 3. Here's a brief description of this. Drawing one card from a deck of 52. Part A here. The description is the probability that A, it's an ace, or B, it's a 9. So to summarize, the probability of A or 9. In the case of B, the probability of an ace or a heart. Make that red, right? And then, let's see if I can get this to fit. I always feel like the tiniest man on earth. When you work at a classroom, right? You have a full-size board that is many times larger than what I have here. Right? Because I'm in my house, of course. But in order to get it to work correctly, you know, I have to crouch a lot, and I have to use these implements that are just very, very large, you know, by normal standard, and cumbersome. Anyhow, the world is a hazard, even in your house. Okay, so the probability here is the probability of a red or a black card. Yeah, it's gonna be funny now. All right. Red or black. And this last one, D, is the probability of a face card or a red card. Technically this heart here. And it looks terrible, but okay. Alright, very Harley Quinn. Alright, now in each of these cases they're asking you, well, verify first whether it's mutually exclusive or not. Alright, so to help summarize, let me just write like this. Alright, ME as in mutually exclusive, alright, or not mutually exclusive. And here, and here, and here. Why? Again, because it dictates which formula you're going to use. I'll go with blue in this case. Alright. Get in the habit again of asking yourself, since you have or types of problems, ask yourself, can these, each circumstance, occur simultaneously? Can a card be both an ace and a 9 at the same time? They can't. All right. No. Right. So they are mutually exclusive. Right. They can't occur simultaneously because an ace is like a 1 technically. Yeah. So it's like, can a card be a 1 and a 9 at the same time? Absolutely not. All right. So therefore, which incarnation of the formula are we going to use? This one, the probability of an ace
plus the probability of a 9. Right? And then we'll calculate it. How many aces are there in a deck of 52? Right? There's 4 out of 52. How many 9s are there? Similarly, there's 4 of them. Right, so if you just simply added them, you would get 8 out of 52, not 32. I just so desperately want this to be 32, but it's not correct. So it would be 2/3 once again. Two 13ths, I should say. Right, simplified. 8 over 52 is correct, but it would be ideal to write things in simplest form, okay? So be mindful of that. If MyLab gives you any bit of trouble, it probably just isn't simplified, okay? This situation, all right? Ask yourself, can these occur simultaneously? Can a card be both an ace and in the suit of a heart? Right? Yes. Right? Yes. Right? So therefore, these are not mutually exclusive. And we're going to borrow that incarnation of the formula then. Right? The one where you have to subtract out so you don't count something more than one time. Right? So the more concise way of writing this would be A or heart is equal to the probability of an ace plus the probability of a heart minus the situation where you have one and the same. Okay, so again, how many cards are aces in a deck of 52? 4 out of 52. How many hearts are there? Not just 4, there's 13 of them technically, right? So it's plus 13. And then, since they coexist in both of these circumstances, the same card, all right, we're going to subtract out those simultaneous events. So how many cards are both an ace and a heart? All right, just one, right? So minus that one instance. All right, the actual ace of hearts. Right. 4 plus 13 is 17. 17 minus 1 is 16. 16 over 52 can be reduced by dividing by 4, I believe. 16 divided by 4 is 4. 52 divided by 4 is 13. So 4 over 13. Okay. Not too bad, right? All right. Moving on. All right. The probability of a card being red or black. All right. Now, can these occur simultaneously? Can a card be both red and black at the same time? All right. Outside of the quantum realm, I don't think so. So, no, they can't be that at the same time. Right. So these are mutually exclusive, which means, again, we're going to be borrowing from this more basic formula, which is the probability of a red card or the probability of a black card is equal to the probability of a red, all right, plus the probability of black. Okay. Now, how many red cards are there in the deck? Half of the deck, right? So that's 26. I'll put this to make it more obvious in blue. There's 26 cards that are red out of 52. That's half of the deck. How many cards are black? Also 26. 26 out of 52. If you add 26 to 26, you're going to get 52 out of 52, which is one whole. Okay. So under these circumstances, the probability of drawing one card that is either red or black, you're guaranteed that it's going to be one or the other. There's a 100% chance of that materializing. This one. Let's see, the probability of a face card or a red card, right? Can a face card, ask yourself, can these occur simultaneously? Can a card be both a face and also red? They definitely can. So if you say yes, then they are not mutually exclusive. Right, which means you're going to use this formula. The probability of a face or a red card is going to be equal to the probability of a face plus the probability of a red minus the situation where they occur one and the same. Face and red. Okay. So how many face cards are there in a deck of 52? There should be 12, I believe. 3 from each suit that are faces. So you have 12 out of 52. How many red cards are there? This is again 26 total. The situation where we're discussing one and the same, where they do occur simultaneously, is accounted for in each of these situations. So to not count them twice, we're going to subtract out those particular examples. How many face cards are in fact red? Right? 6 out of 52. That's a 25. Right. So 12 plus 26 is 38. 38 minus 6 is 32. 32 out of 52. You could divide each of those by 4 to simplify at least. Right? Would be 8 over 13. Okay, overall. Okay. This is just to illustrate the repetitiousness of it, to illustrate the thought process that you must go through basically every time, just to distinguish, which formula you can use. Now, having said that, let me see, is it appropriate to do 4 yet? No, okay. So let me go back to the sheet from before, basically this one, and I'm going to describe these two formulae. And then we'll do 4, 5, and 6, and 7. Pardon me while I get a drink. This grapefruit juice wakes me up better than coffee did. Now, make this more conducive. Let's see. The width of my camera is basically going to be the problem here. Alright, that's probably as good as it's going to get. Let me just duplicate the formulas so you see them all at once. The probability of A or B mutually exclusive is equal to the probability of A plus the probability of B. the probability of not mutually exclusive is the probability of A or B almost the same. A plus B, and then subtracting out those occasions where they would be counted more than once. And B. Alright, this is established. Alright, now, these situations, alright, the and statements, they don't always unfortunately say the word and, right? So what, in this case, you have to, in order to decide, if you don't see or, right, it's, in this section, it's probably this situation, right? But in general, to be careful, what you want to do is ask yourself whether the events are dependent or independent, right? These are, in general, consecutive events. Meaning one follows the other. Right? If you know that you're dealing with consecutive events, right, they could be dependent or they could be independent. If they're truly independent, it means that the first has no bearing on the second at all. And you will very likely see this phrase, with replacement. Right? That implies this situation. If the first does affect the second event, all right, meaning usually what that means is that it reduces the amount from which you have to choose, they will use this phrase, with replacement. Right? That implies this situation. All right? These are consecutive events. Right? One occurs after the other. The or situation, these are potentially simultaneous. Right? Right. They're not really consecutive. I'm sort of struggling to find a word to distinguish it from that. I wouldn't call these consecutive. You might say that they're basically contemporaneous. Right? Right? We're really considering them at the same time. So, if it helps, make that distinction, all right? These are definitely one thing follows another. These are more or less things that can occur at the same time. What you really have to get into the weeds about is whether or not they can in fact coexist, all right, in the same body. You know, this or this. All right. Being mutually exclusive or not mutually exclusive. Okay? Now, the formula that you'll see in this case, and it would be most appropriate to use the word and, you will see this. The probability of A and B. I'm kind of writing it stacked in this case because I'm short on space. All right. In fact, why don't I do myself a favor, since this is already established. Just zoom in on this so I don't have to struggle. All right. I'm going to scoot this over, and I hope you will forgive me, and just blow this up. Consecutive events again. All right. If you see this phrase without replacement, the probability of A and B is just two things multiplied. Right? But I'm going to add a little bit to this formula that your textbook neglects to for a reason. The probability of A, the first thing, and then the probability of B given A occurred. I really feel that that would be the better way to write this. Because if the second is affected by the first, the condition would be different than this situation, slightly. All right? The probability of B given A occurred. My blue is getting a little terrible. Now in this situation, let's see if this works. With replacement, that means essentially that the the first has no bearing on the second. It doesn't affect it at all. So it's actually a less complicated formula. I will get out of the way in a second, I promise. A and B is just the probability of A times the probability of B. Right? Which is why these are grouped together as the multiplication rules. Right, versus the addition rules. Multiplying in both of these cases. This one is a slightly more stricter situation. B given A occurred. To was. Okay. All right. Now, an example for this one. This is aggravate me if I don't. An example for this would be something like the probability. I'll do it in red. Of drawing a queen and an ace with without replacement. The probability of drawing a queen, Q, and an ace without replacing the card after you picked out the first one. So they're even if it's not the same card, right? There's going to be some bearing on the second, all right, because of the first. All right? So to borrow this model and adapt it to just these letters instead, all right, the probability of Q and A is equal to the probability of Q, since that happened to be the first thing that occurred, right, times the probability of A given Q occurred. Okay? Now, assuming that you have a regular deck of 52 playing cards, how many queens are in a standard deck of 52 playing cards? It would be 4 out of 52. Right? This is the first thing, so those are the conditions. 4 out of 52. Since this has some bearing because the card was not put back, right? How many total cards are there now in this situation? There aren't 52 cards anymore. There's one less, so it's 51. Right. How many aces are there in a deck of 52? All right. There's still 4. All right. Okay. If the situation were about 2 queens instead, then you would diminish this to 3 as well. But we're not talking about a second queen. We're just sticking with an ace in this case. All right. So notice that you have now, unfortunately, different denominators, right? But you're multiplying, you're not adding or subtracting in this case. So what you're going to end up with is something that's really a large figure. If you could simplify, if you're doing this by hand, you could use a calculator certainly, but if you're going to do this by hand, do yourself the favor All right, don't just do brute force 4 times 4, 52 times 51, because you're going to get something that is well outside the realm of the familiar. All right, if you simplify first, you make the simplifying, you make the answer a little bit easy to get to. All right, 4 and 52, it may not be too obvious, except if you've done a lot of these problems. They have a common factor, which means you could simplify both of them. All right, you could either do it diagonally, or you could do one above the other. 4 divided by itself is 1, 52 divided by 4 is 13, right? And now you're kind of stuck with the leftovers, right? Which means 1 times 4 is 4, and 13 times 51 is 663, I believe. Is that right? Let me just verify. 13 times 51. Yeah, it's terrible, but it's true. There are limitations to this type of a calculator that you guys have, all right, but it probably can simplify this. If you were to hit 4 and then this button ABC, you can enter things in the style of a fraction. And if you type 663 like this on your screen and then hit enter, if it was simplifiable, then it would reduce it automatically. But if it doesn't, you're pretty much stuck with it. You could alternatively just sit here and whittle away using rules of divisibility, but I took the time to simplify up front, so less likely. All right. So that's that example. All right, without replacement, these situations described are a dependent situation. Okay, now let's get to this one. This one is technically easier, all right, because, and this is more akin, if you notice, to the counting principle, all right, except that you're going to be dealing with actual probabilities, which means a fraction times a fraction rather than a whole number times a whole number, all right. You're not looking just merely for the total number of outcomes in the sample space, the sort of quasi-combinations, if you will. You are, in this case, trying to get an actual probability. Right? So here's an example to summarize this. Right? The probability of drawing let's see, a queen and an ace with replacement. Might as well do that. Have some inkling about it already, and you'll see how this affects the question, the answer. All right. In this case, all right, to adapt this, it would be the probability of Q, as that's mentioned first, and A for aces. With replacement means that one has no bearing on the other. So the probability of Q times the probability of A. Right. How many queens are there in a deck of 52 playing cards? There are 4, we've established many times. All right. How many aces are there in a deck of 52 playing cards? There's still 4. But since the card was put back, the total pool of cards, the number in the set, remains at 52, not 51. Right? That's the difference. Come on. Right? So what do you end up with in this case? Much larger figure. I would, again, if you're doing this at all by hand, or even if you are using a calculator, there's limitations. Right? Very large denominators. Yeah, the graphing calculator would be better, but you're not supposed to use that to begin with. Simplified, this is 1/13 now. All right, and the same thing here. 1/13, which means that it's 1 times 1, and 13 times 13 is 169. So 1 over 169. All right. If you got 16 over 20, pardon me, 2704, it will reduce to that. All right. Okay. So now you have established 4 formulas. Okay. Just be careful that you use them in the appropriate situations. All right. We're going to do example 4, 5, 6, and 7 now. All right. And it might be a blend. It will probably be a blend of these two mostly. All right. We'll see. Let me see if I can get away with projecting here. Examples here. All right. I think before I can probably get away with just writing, not moving it around too much. It's a little blurry, but let me read it too. All right, example 4 is 2 cards are to be selected with replacement. All right, if you see again the phrase with or without replacement, as you do here, all right, red alert, all right, you're probably dealing with a dependent or independent situation, in which case you're dealing with the multiplication rules. So, from a deck of cards, determine the probability that 2 spades will be selected. All right, so we're basically talking about consecutive events here. All right, and I'm going to try to abbreviate what the description is here. We're going to calculate the probability of a spade. I should use black, right? That would be appropriate. The probability of a spade, and then a second spade. If you want to distinguish one from the other, you could get fancy, right? You could put subscripts, spade number 1, spade number 2. That's up to you. All right, with replacement means this situation, although I don't have it written here. With replacement implies independent equations, right? One has no bearing on the other because the card was put back, right? So this is equal to the probability of the first spade times the probability of the second spade. Right? How many spades are there on a deck of 52? There are, I want to say 13 out of 52. All right? And since we're doing this with replacement, and there is no effect on the second drawer, it's still the same figure, 13 out of 52. Okay, so it's just multiplication, they're independent. Consecutive events, 13 to you. If you could simplify, I would. It may be not quite as obvious, but 13 times 4 is 52. So what you have here to simplify is that this is 1 over 4 really. And this would be the same thing. So 1 times 1 is 1, and 4 times 4 is 16. Now, what they do in the case of question 5 is they go for the other situation where you have without replacement. So we're talking about consecutive events again. I'm sorry that this is down here, but example 5 is 2 cards are to be selected without replacement. Train your eye on that. From a deck of cards, determine the probability that 2 spades will be selected. It's almost exactly the same description, but with this phrase tucked into it, without replacement, which means that these are dependent. Dependent events. Alright, so the probability of the first spade and the probability of the second spade. You could use S's if you'd like, you know, I'm just using the symbol. Would be the probability of the first times the probability of the second given the first occurred. The second event is dependent upon the situation of the first. Okay? Sorry if it's a little bit messy. I hope that isn't too difficult to see. But to describe it, all right, the first event is completely, you know, no worries, just answer the probability. How many spades are there in a deck of 52? All right? In this scenario, there's still that 13 out of 52. All right? In this situation, because the card, without replacing, means the card was not put back. All right? Let's answer this. How many cards total are there out of 52 if you didn't put one back? There's already 51, all right? Hypothetically, if one of the cards drawn out of the 13 was in fact a spade, how many spades are left over now as well? There's 12, right? So it's a sort of a double whammy, right? Now you've reduced the pool of total, but you've also reduced the amount that is spades to draw from. This is different from the problem with queens and aces because we weren't talking about a second queen at that point. Right? In this case, we're talking about 2 events that are dependent. Right? So the fraction reduces to 12 over 51. Okay. Again, do yourself the favor, try to simplify where you can. This is really 1 over 4. This is divisible by 3, all right, 51, because of the sum of the digits being 6, all right? And so is 12, so you can reduce that as well. 12 divided by 3 is 4, right? And there happens to be a 4 over here. And 51 divided by 3 is, I believe, 17. 3 goes into this twice, pardon me, 1 time. With 2 leftovers, yeah, 17, all right? 4 over 17, now, you could simplify again. Right? There's a 4 down here below this line, and there's a 4 up here above the line. So the 4s will cancel. Right? So it's 1 times 1 and 1 times 17. Right? This is 1 out of 17 overall. Right? Simplified. Okay? And nothing wrong with doing brute force 13 times 12. You get a big number, but you could whittle it down if you have the endurance, right? Just remember you have rules of divisibility to lean on or other techniques, all right? Ideally, you would want to use the greatest common factor, but sometimes it's not so obvious.
Okay.
Here's 6.
Being a little anal retentive right now, but I'm gonna just not to distract. I'm gonna pull up my bootleg paint here, and just to establish a white surface, which I will put above this. Okay. All right. Now, in this case of example 6, you're just asked to decide whether the events are dependent or independent, and then calculate. So. You have 100 people attending a charity benefit to raise money for cancer research.
3 people in attendance will be selected at random without replacement. Right. Again, you see this phrase, without replacement, red alert. You're dealing with the AND type multiplication rules. All right. And each will be awarded 1 door prize. All right. Are the events selecting the 3 people who will be awarded the door prize independent or dependent? All right. Well, if you have this phrase, without replacement, that means that these are dependent. Events. All right. Because, right, the subsequent events are dependent, are affected by the first, by earlier events. Okay? The subsequent events are affected by the earlier events. Okay? If you had put, we're talking about people here, we're not talking about cards. Imagine, I assume their names are put into a hat or something, right? It'd be kind of funny if they just decided to grab a person and put them in a giant hat, All right. Here's how you would adapt the formula that we have for the situation of dependent events, all right? If the model that we have is for 2 things, we can expand it to a 3rd thing. So it was probability of A and B, right? So what we'll say is the probability of A and B and C. Now, having a relationship to intersections, all right? I wonder if you could use the horseshoe shape in this case. It's not really important right now, but that to me is to extrapolate on this. It probably is okay. Anyhow, the model, when we had just 2 of these, was, okay, calculate the probability of A all by itself, all right? Then calculate the probability of B given A occurred. Times, right? And since we now have a 3rd situation here, all right, we're going to have another factor here, the probability of C, but it's going to be given the 2 first events occurred. So given A and B occurred. So by the time you get to the 3rd person in these consecutive events, right, the fraction will change. Okay? We're talking about 100 people, right? All right, 3 randomly selected, or 3 selected. Those are the conditions, basically. All right, now, the conditions are going to change as we progress. In the case of the first person, all right, nobody has been selected yet, right? What would the fraction look like for this particular individual, all right? There's 100 people to draw from, so the denominator is definitely 100, right? How many unique individuals, let's call this Albert here, right? How many Alberts are out of the 100? 1, right? Hopefully. Right? By name, anyway. I'm talking about the soul, not the name, really. How many of this soul of Albert are there? 1 out of 100. Okay. So now we're going to multiply and take into consideration Albert's effect on the subsequent draws here. Okay, now in this situation, the probability of Bert, all right, given that Albert has already occurred here, all right, is there still 100 people to draw from, all right? If they use this phrase without replacement, no, they didn't put Albert back in the pile. Because again, funny to me is I'm a weirdo that you just grab a person and stuff them in a large hat. It doesn't work that way. There's 99 people. Okay. Now, how many of them are Bert? All right. The soul that is Bert. It's 1 out of 99, right? All right. Moving on. See, math can be fun, right? If you have a demented sense of humor. All right. So. Life can be funny. This is a dud. Green, I hate you. I like the color, I just hate the marker. Alright, now, when we get to, let's call this Christine here, alright? What is the probability of Christine given that Albert and Bert have already occurred, these other two people, alright? Is there still 99 people? No, now it's even one less, right? So it's 98 people. Alright, now, nonetheless, how many souls are there that are this particular Christine person? Alright, just this one individual, alright? Christine with a C, alright? Alright, so there you have it, right? 3 fractions that are multiplied, so you're going to have something pretty large in terms of a denominator, alright? There's no way that you can simplify, unfortunately, because you have 1s as the numerators, so you kind of get stuck with it, alright? 1 times 1 times 1 means that you have 1 on top, yay. Alright, 100 times 99 is 9,900. 9,900 times 98 is going to be huge. Alright, so let's see what it is. 100 times 99 times 98. Alright, 970,200. Right. Okay. Which is like, in terms of a percentage, if you divided this by this, you would have zeros to the 1, 2, 3, 4, 5, 6 decimal places, and before you hit a 1, all right? There's 5 zeros. All right. So even as a percentage, it would be like minuscule. Okay. All right. Now we do number 7. Which is multi-part. Okay. I might turn off the projector for this one. Let me see. Okay. Let me read it to you. Here's another drug reaction. Do you get the feeling that whoever writes this is really into drugs? Writes these problems, you know? Unless this was for, you know, pharmacology, you know, I wouldn't understand it. Alright? I'm getting sick of these drug reaction things. Come on, come up with a better thing here. Alright. A new medicine, alright, was given to a sample of 25 people of Dr. Cleary's, good name for a doctor, alright, is all clear, alright, patients with the flu symptoms, alright, of the total, alright, 19 people are selected at random. 19 people react favorably, right, to the drug, and 2 react unfavorably, and 4 were unaffected. Okay, 3 of these patients are selected at random. Okay, determine the probability of each of the following conditions. All right, we have all the information here, and I'm going to try to sort of space this out on my board here and turn off the projector. All right, and now just describe them briefly. Okay, so curtain, okay, lamp, and we continue. Let me just do this. It's 4 parts, A, B, C, D. So I'll cut this in half. All right. We'll do A here and then B here. Proceed. The conditions described by A, right? They want you to calculate essentially this. The probability that all react favorably. Okay. Now notice that there is no and or in this case. So if you're talking about 3 people selected at random, right? These are consecutive events though. I mean, it's very subtle, but it might be implied that this is without replacement. So as we progress, that means that the conditions are going to change. As far as the formula is concerned, in this situation, let's call these three people again A, B, and C. A, B, and C, just for the sake of simplicity. All right. The probability that all react favorably. All right. Let's see. First person, second person, third person. Maybe that would be better, just not to confuse things. First, second, third. Generalized. All right. They're going to be a ratio, fraction, probability in three cases. All right. Since we're dealing with consecutive events, let's assume to start with that we're dealing with multiplication. All right. If we assume that it's without replacement, all right, and that would make sense in the case of this drug test. One is going to have an effect upon the other. So without replacements, which means that these are dependent. Okay. How many people are there total? That's 19 plus 2 plus 4. That's 25 total. So the first person, when they're selected, is out of a pool of 25. Right? The second person is, since there's without replacement, is going to be one number less than that. So it's going to be out of 24. Right? And then when you get to the third person, again, without replacement dependency, you're going to have out of 23. All right. Now, of the type that are the favorable type, all right, there's 19 to start with, all right? But again, if we're considering that this is favorable, and this is favorable, and this is favorable at all three times, all right, then the pool from which they're going to choose people out of 19 is going to also diminish as we go across here. So 19 out of 25, the total shrinks, and the amount out of 19 shrinks to 18, all right? And then when you get to the third person, because it is affected by the first two things, the total shrinks again, and then the pool from out of 19 shrinks again, which means that you get to 17. All right. If you end up multiplying 19 times 18 times 20 to 17, 19 times 18 times 20, 19 times 18 times 17, you're going to get a huge number. It's like 5,800 something. Anyhow, so what eventually you will get, I wonder if you can simplify this. That's a prime number. Nope. These are both even. You can simplify these two. All right. They're both divisible by 6. All right. So let's see. 6 goes into this 3 times. 6 goes into this 4 times. So that one you could at least reduce. I think that's pretty much it. You really can't get away with too much else. So 19 times 3 times 17, yuck. Yep, that is correct. It's going to be this awful figure, 969 out of the leftover 25 times 4 is 100. 100 times 23 is 2,300. Right. Which is something like 42% if you changed it to a percentage. Okay. All right. Moving on. Situation B here. All right. What they're asking in the case of B is these conditions. The first person is going to react favorably. The second and the third unfavorably. Pardon me. The second is unfavorable, and the third is unaffected. Okay. We're still dealing with dependent events here. All right, because the total number of people is going to shrink. All right. But the numerators may or may not be changed, so let's analyze each one of these. All right. The fraction here, the fraction here, the fraction here. Okay. If again we're starting off with first person, how many are there still to begin with? 25. All right. How many would there be when you're picking the second person? There would be 24 again, it would shrink. All right. How many would there be by the time you get to the third person? There should be 23. Okay. But now we're describing different circumstances. These were all favorable to begin with, and this is more or less one of each type, each classification. So in the first case, the number of favorable people will be 19, as it would be. All right. That doesn't really affect the top of this fraction here. So if we're considering unfavorable people, who do you have to pull from here? In this case, it's just 2. All right. And the third one, unaffected, would be 4. All right. Because we didn't pull from that type. All right. The only thing that is dependent is the total in this case. Okay. All right. Again, I would try to simplify if it's possible. Sometimes it's not. You can simplify these. Both divisible by 2. That becomes 1. This becomes 12. Then you can simplify 4 and 12. Let's see. 4 goes in divided by itself is 1. 12 divided by 4 is 3 left over here. All right. You can't really finagle any more than that. It would be 19 times 1 times 1. Which means that this would be 19 on top. All right, and as far as the bottom is concerned, it would be 25 times 3, which is 75, and then 75 times 23, which is what? 75 times 23, 1725. Which is like 1.1% if you changed it to a percentage. Okay. All right. Next one. C. I'll put here. Tenacious blue. Question C. D will go here. The conditions here described. All right. Let's see. No patients react. None favorably. No patient reacted favorably, so none unfavorably, just to be more concise. None favorably, sorry. Still, the initial condition is 3 selected. All right. And we are going to assume without replacement. Okay. So we're going to consider first person, second person, third person. Start with maybe the total because it'll be the easier thing. This is not favorable. this second person would also be not favorable, and then this person would also be not favorable. All right, now there's 25 people in this case. And then naturally the total would be, when you get to this one, it should be one less than that again, which would be 24. And then when you get to the third person, again, it would be out of 23. All right, but what is going to be a little funky here is how we establish the tops in this case. All right, how many people in these described conditions here are just not favorable to begin with? We're not choosing from 19, we're choosing from the combined unfavorable, because that's not favorable, and unaffected, because that's not favorable also. How many are there combined here? It would be 6, right, to start with, right? Now, because we're talking about dependent events, though, all right, in this case, yes, definitely the denominators are going to shrink, right, because you have less and less of a pool of resources of people to draw from, all right? But what is also simultaneously going to shrink is this figure as well. This person is not favorable, right? But this is given, first occurred. So what's 1 less than 6? 5 in this case, right? And then when you get to the third person, this is given, first and second occurred already. So what's 2 less than 6? All right, 4. All right. So again, try to whittle it down. All right. Once you've established this, you can do 6 and 4 here, 24 here. You can do 4 and 24 in theory as well. If you did that, let's just say you did 4 divided by 4 is 1, 24 divided by 4 is 6. The 6's would cancel, all right, and simultaneously this 5 would be 1, and this would be 5. All right, so you have a slew of 1s across the top. This would be equal to 1 as the numerator. 1 times 1 times 1. 5 times 1 is 5. 5 times 23 is 115. So yeah. All right, 115. 1 out of 115, I should say. Okay, the D. This is where you could dig up a formula from earlier, right, and borrow some of the work that you've already done. So in this case, what is described at least one patient reacted favorably. The probability of at least one favorable. Now, if you remember from the last section, in 11.4, right, there's a formula that is very similar to the complement formula. It's more or less the same thing, rearranged. There was this formula. The probability of an event at least once can be calculated by subtracting from a whole. So the probability of the event happening at least once would be equal to the difference of the whole possibilities minus the probability the event does not happen. This is from section 11.4. Again, it's sort of the complement formula, just rearranged. All right. Instead of finding the complement, which would be not something, we're finding at least once. All right. Now, we just actually calculated part of this. All right. This is at least one favorable. All right, what we have here is not favorable at all. All right, so what we could do is squeak this in here. 1 out of 115 subtracted from 1 whole. All right, because we already did the work for that. All right. Anyhow, if you're going to subtract from the whole, remember, just make 1 a common denominator, so it would be 1 over 115, and then to make it truly 1 whole, it would be something over itself. So it would be 115 1/15ths. Right, it's an awkward way of speaking, right? Anyhow, what is 115 minus 1? 114 out of 115. Right, which is a percentage of something like 99%, right? How come? Because out of all of these people in this drug trial, this is clearly the most, right? 19 people reacted favorably to the substance. Okay? All right, that is that. So, if you are following along according to the schedule, what you want to do technically now for homework is to do section 11.5 in my lab. Right, and then you are all squared away. Okay? So please work on that. All right? I'll see you again on Thursday. Okay? Be careful out there.